Hello, I'm Rebecca Barnes. Welcome to the Science ESA vodcast. In this episode, we would take a closer look at Planck, a European Space Agency mission built to detect radiation from the microwave portion of the electromagnetic spectrum. This mission will help find answers to some of the most important questions in modern science. What is the universe made of? How did the universe begin? How did it evolve into the state we observe today? And what is in store for its future? The universe that we live in fact, space itself, is expanding. This is known from Hubble's law. If the universe is now expanding, this means that at some point in the past, all energy and matter must have been considerably hotter and more densely packed than it is today. This model of the beginning of our universe is known as the Big Bang. However, there are a number of things the Big Bang can't explain. For example, consider the very distant regions of space that are in opposite directions of the sky. They are so far apart that if you reverse time and the expansion of the universe, as described by the Big Bang model, you find that the light travel time between them exceeds the age of the universe. Something else is needed to explain this, and the theory that is widely accepted today describes a phenomena known as inflation.
Our universe is about 14 billion years old. In the beginning, a process called inflation caused the universe to expand exponentially. At the end of the short inflation period, a very hot, dense, and rapidly expanding plasma of fundamental particles was left behind. As this plasma expanded further, it cooled and generated the right conditions to form a soup of the building blocks of all matter, quarks, and electrons. After about 300,000 years, the first atoms formed, hydrogen and helium. Initially, these atoms were ionized. Photons were continually scattered by the free electrons and trapped inside the plasma. Further expansion cooled the plasma, enabling atoms to capture and bind electrons. At this time, the universe became transparent. The liberated photons were able to propagate freely in all directions. By now, the universe had cooled to around 3000 Kelvin, and so the energy of the first free photons was equivalent to infrared wavelengths. Since the universe became transparent, it has expanded more than 1,000 times, and the sky has cooled to just 2.7 Kelvin. The wavelength of these ancient photons has now stretched to microwaves. Despite their long journey towards us, these photons still preserve the physical information imprinted on them in the young, opaque universe. Today, they are detected as the cosmic microwave background, a relic from the Big Bang.
In 1965, Arno Penzias and Robert Wilson observed a continuous background radio signal that was spread over the entire sky. They had accidentally discovered the cosmic microwave background. Since then, two satellites, COBE, the Cosmic Background Explorer, and WMAP, the Wilkinson Microwave and Isotropy Probe, along with a number of balloon-borne experiments, have mapped the cosmic microwave background with increasing precision. After 40 years of study, it is now known that there are very tiny temperature variations right across the cosmic microwave background. These directly relate to the density of the plasma at the time light first propagated freely in the early universe. Denser areas eventually coalesced into the large-scale structures that we see today, stars and galaxies. What's more, these variations have been found to follow distinctive patterns that fit predictions made by cosmological theory and have been used to estimate the age, composition, and geometry of the universe. These experiments have also provided convincing evidence that our universe is dominated by mysterious dark energy and dark matter. There are still many unanswered questions. What caused the density variations in the early universe? Did the universe go through an inflation period? If so, what was its nature and what caused the rapid expansion? What is the nature of dark energy and dark matter? ESA's Planck mission will help to answer these questions about the nature of the early universe and much more. What makes Planck different to previous missions? Let's find out from the experts involved.
COBE and then WMAP have been setting the stage in a very clear way, in a very firm way. So we, in a sense, we know what to look for. Planck is the third generation satellite, which would have a much greater sensitivity and angular resolution in the sky to see the tiny details that will tell us about how the universe was and what its evolution has been in these 14 billion years.
There are some things which are very definite prediction that we will be able to do with Planck and which were not possible with previous satellites. And one of them is measuring something which is even more difficult than just detecting this fluctuation of the microwave background, the intensity, seeing where the intensity is stronger than at other places, but looking at what physicists are calling the polarization. Polarized glasses when sunglasses, the same type of principle where you observe basically how the light is vibrating, what direction is it vibrating into. And this extra information, there was very specific prediction of inflation for that. So if we find this signature, that will be not a proof, never completely sure, but a very strong indication that there was this period of inflation.
The Planck spacecraft carries a payload of two highly sensitive instruments, the Low Frequency Instrument, or LFI, and the High Frequency Instrument, or HFI. In total, 74 detectors covering 9 frequency channels will be used in this ESA mission to map the cosmic microwave background. The High Frequency Instrument is an array of 52 bolometric horn-shaped detectors that convert radiation into heat. The detectors work in 6 frequency channels centered between 100 and 857 gigahertz. This state-of-the-art instrument is like no other currently operating in space. The low-frequency instrument consists of 22 radio receivers that are tuned to 3 frequency channels between 30 and 70 gigahertz. They work like transistor radios, amplifying the signal collected by the telescope and converting it to a voltage. In order to detect and precisely measure the tiny fluctuations in the cosmic microwave background, the detectors must be cooled. The LFI is cooled to 20 Kelvin. The HFI is also cooled, but to 0.1 Kelvin, just 1/10 of a degree above absolute zero. The innovative cooling system wraps around the HFI in progressively cooler layers, each protecting the next part of the system from radiation and heat given off by the warmer outer layers.
These are V-grooves, cone-shaped reflecting surfaces that insulate the instruments, providing the first stage of the cooling process down to 50 Kelvin. The next layer cools both instruments, the LFI to 20 Kelvin and the HFI to 18 Kelvin. This is achieved through a sorption cooler, which thermally cycles compressors that are filled with metal hydride to absorb and desorb hydrogen gas. To reach the temperature required for the HFI, a Joule-Thomson refrigerator driven by mechanical compressors is used. This employs helium gas to reduce the temperature to 4 Kelvin. The innermost layer of the cooling system is a dilution refrigerator that mixes together 2 isotopes of helium. A change in enthalpy occurs during dilution, which cools the helium mixture to just 0.1 Kelvin. The cooling system, detectors, and the mirrors sit on top of a service module, which contains all the hardware the spacecraft needs to function. A solar panel at the base of the spacecraft provides power and protection from direct sunlight. Planck has 2 reflector mirrors that gather and focus light onto the detectors. The telescope and instruments are surrounded by a large baffle. The baffle is used to radiate heat, generated by the focal plane of the detectors out into space. It also provides the instrument coolers with a stable and cold background environment.
To ensure data collected is as accurate as possible, Planck's orbit is at the second Lagrangian point, known as L2. Here, 3 forces balance: the Earth's gravity, the Sun's gravity, and the centripetal force of the rotating system. L2 is located about 1.5 million kilometers away from Earth. That's nearly 4 times further from us than the Moon. From this location, Planck keeps its payload in the shade and the solar array always facing towards the Sun. A huge challenge faced when measuring the cosmic microwave background is light from other microwave sources straying onto the detectors. For example, the Earth is 99 times more luminous in the microwave than the cosmic microwave background. By launching into a far Earth orbit, this problem is minimized, as the angular size of the Earth is considerably reduced. From L2, the Earth looks the same size as the full moon does when viewed from Earth.
The Planck spacecraft spins once a minute, and as it does, the field of view sweeps a ring of 170 degrees in diameter. Planck can scan the entire sky in 6 months. To produce a map of the cosmic microwave background, the data must be cleaned of all sources of noise and thoroughly processed. An advantage of using many frequencies to detect the cosmic microwave background is that sources of microwaves that lie in the foreground can be stripped away with greater precision. When maps of the cosmic microwave background are first viewed, you notice there is an asymmetry known as the cosmic dipole. This is due to the Doppler effect caused by the motion of the Earth and the Sun with respect to the background radiation. Removing the dipole reveals the temperature variations present across the entire sky. Here, microwaves emitted by the Milky Way are visible as a red band in front of the cosmic microwave background. This signal can also be removed in the process, providing useful information about our galaxy. Away from the plane of the Milky Way, among variations or anisotropies of the cosmic microwave background, lurks microwave emission from distant galaxies and galaxy clusters. Each class of object has a distinct spectrum which allows it to be distinguished from the rest and hence removed.
Once all of this astrophysical noise has been removed, the most notable features remaining in the maps are small characteristic spots. Data collected by Planck will be carefully analysed in a number of different ways to look for specific patterns of spots and for evidence of polarised light.
What I would like that Planck will discover is what I defined the bipolarization of the cosmic microwave background, the polarized field in the magnetic polarized field of the CMB, because this would mean that we understand the origin of our universe, we understand the gravitational waves, we understand the quantum fluctuations which at the very beginning, just after the Big Bang, gave rise to the structure that we see today in the universe. This will be a Nobel Prize, not to me, but to the team.
There are lots of questions that Planck will answer by itself. Okay. Now, it's also an enabling experiment for future generations, and it's instructive that most of the science case of the large experiments, proposed in the next 10 to 20 years are already taken Planck for granted as a success, and they are all trying to sort of focus how they can build up on this to answer the next round of questions.
In this vodcast, we have taken a closer look at the Planck mission and seen how, by detecting the first light of the universe, it will provide the information needed to tackle some of astronomy's big questions. Now, we will just have to wait patiently and look forward to the exciting results. I'm Rebecca Barnes. Thank you for watching this Science ESA vodcast.